Okay, so what we want to do is look at more complex kinds of solids that we would integrate a three-variable function over. So if we take a look at this solid here, which I'm calling E, this falls under the category of what we call a type 1 solid. Within this solid E, all of the points within this solid are the z coordinates of those points are trapped between two variable functions of x and y. So in other words, I'm going to think of this solid E as having a surface on top and a surface on bottom that act as the upper and lower bounds for this solid. And because the top and bottom surfaces of this solid are surfaces, the graphs of surfaces oftentimes come from functions of the form f of x, y. So if we can represent the top and bottom surface as two variable functions, then we can refer to this as a type 1 solid. Notice that if I were to project the points within this solid onto the xy plane, it also creates a plane region D, which we're going to need. So that plane region you can think of as kind of like the shadow of this solid if you shone a light straight down into the xy plane. But that's the projection of that solid into the xy plane. So a way of describing this set this solid as a set is to say that it's the set of all x, y, z, such that x, y are in this plane region D, and z, the z coordinate, is trapped between those two functions. In this case, I'm calling them u1 xy, which is the function giving me the lower surface, and u2 of xy giving me the top surface. How then do we take this set and turn this into an integral? Well, the idea is to take our triple integral and reduce it to a double integral. The way that we do that is we use this set to determine the limits of integration. X and y, the xy coordinates of any of these ordered triples belong to this set D. So two variables, that's going to reduce to a double integral over that region D. And then our function z, our limits on z are given by these two functions of x and y. Those become the limits of integration on this partial integral here. And just to be clear, with this partial integral, f of x, y, z, dz, is just like how we did partial integrals when we introduced them towards the beginning of chapter 15, which is we hold all the variables except for z constant, if this is a dz here. And then we integrate with respect to z. And when we plug in our limits of integration, those limits will look like functions of x and y. And just as a reminder, even if the functions don't explicitly contain x or y, we can still think of them as functions of x and y. For example, u2 of xy might equal x squared. Even though the y is not present there, we can interpret it as a function of x and y. They can equal constants as well. So because these plane regions D also fall under a couple of different categories, that gives us two little subcases of type 1 solids that we could consider. So again, a type 1 solid is a solid where we have a surface on top and a surface on bottom, both given by functions of x and y. And then the projection of that surface gives us this plane region. The projection into the xy plane gives us this plane region D. Now that plane region D can be a lot of different types of regions, but the two that we consider are the type 1 and type 2 plane regions, which we've already talked about with double integrals. So that leads to these two possibilities. The plane region D might be a type 1 region, which means that it's bounded, y is bounded by two functions of x, or it could be a type 2 region where x is bounded by two functions of y. So for that reason, in these problems, a lot of the triple integrals you're going to evaluate, you're going to be sketching at least two different graphs. One for the solid, and one for the region that the solid is projecting in, the projection of that region. Sorry, let me say that differently. the region that we get by projecting that solid into the xy plane. Once you've drawn that region, we then interpret it as either a type 1 or a type 2 region. But notice the reason we need to do that is because up here, once you've evaluated this integral right here, just that inner integral, and plugged in these limits of integration for your z, the result is going to be a function of only x and y. Once that becomes a function of x and y, now we're looking at a double integral. And we have several techniques now for evaluating double integrals. If that double integral is a type 1 region, then your triple integral will reduce to this. Notice again, the inner integral you'll work out first. It's going to become a function of x and y. That gets passed along to the second integral, which is has limits that are functions of x. We're integrating with respect to y, and then it gets passed on to that third integral there. And this is what it would look like in a type 2 case. So I want to work through an example where we need to use this. And it may take more time than I have for this video to do this example, so we'll get as far as we can here. In this case, we're looking for the triple integral over the solid t. And the function that we're integrating is xz. T is given as a description. It's a tetrahedron with vertices shown here. So to figure out where to start, I'm going to try and sketch that tetrahedron. One thing I do notice is that the coordinates of all of these points are non-negative, which tells me that the entire tetrahedron should be contained in the first octant. That's useful because it means I don't have to draw quite as much. I could just focus on the first quadrant right here. Okay, so 0, 0, 0, that's the origin. We do have one point right there. At the origin, I have one at 1, 0, 1. That's x and z are both equal to 1. Y is equal to 0. That means this is a point in the xz plane. So I'm going to make this a 1 and a 1. And we'll say that that's the point 1, 0, 1 right there. And then 0, 1, 1, that's y and z that are both equal to 1. That means we're looking in the yz plane for this point. So I'm going to put that one right there. There's my point 0, 1, 1. And then finally we have a point at 0, 0, 1. X and y are both 0. That puts this on the z-axis at 1, which is right there. So the tetrahedron is going to be the solid that joins all of these points. Let's join these two as well. Okay, that's our tetrahedron T. Now, the next thing we need to do is determine how we would set up limits of integration for this thing. But typically what we want to do is accomplish that by setting up a set that describes this region. So if I were to think of this as a type 1 solid and project this solid down into the xy plane, I could see that the projection is going to look the same as this top triangular face. It's just going to project straight down to here. And I'm going to call that the region D. Now, it's not very easy to see the region D from here. So what I'm going to do is graph in the xy plane that same region. I know that it has x and y intercepts both at 1. This is the region D, and the equation for this is y equals 1 minus x. It's an easy one to come up with. Okay, so now what I want to do is start trying to describe this region. So again, the way that we describe the set T, it's the set of all points x, y, z, such that x and y both belong to the set D, which we'll get another description for by looking at this region, but I'm going to wait on that. And then z is bounded by two surfaces. Now, determining these two surfaces can be kind of difficult, especially the first couple of triple integrals that you do. So you have to think of what surfaces this tetrahedron is made up of. It has 4. That's what tetra means, 4. four surfaces. There's one that lies in the z plane here on the side. There's another one that lies here in the yz plane. There's this top region right here, this top surface, and then there's the surface that kind of slants down into the origin right there. So the way that you determine which surface is on top and which surface is on the bottom, in the case of a type 1 solid, the way I like to think of it is I imagine taking a marble or something and treating this tetrahedron as if it's hollow. Hold the marble at the very top of this tetrahedron or this solid. That's going to be the upper bound for my z. If I were to drop that marble down inside this hollowed out tetrahedron, what surface would it land on? That's going to represent the lower surface, because that's going to put bounds on z. It would land on this slanted region. It's not too difficult to imagine. So what I need are functions that describe the top face of this tetrahedron and then the face that slants into this origin here. Well, the top is easy enough because that's a plane that's parallel to the xy plane and cuts through 1 on the z-axis. That makes that top surface z equals 1. The surface down here is also a plane. It's a triangular piece of a plane. The question is, what equation do we have for that plane? There's different ways to come up with it, but if we think back to chapter 12, how we came up with equations of a plane, if I can find a normal vector to that plane, that I can use that to come up with the equation. So thinking back to chapter 12, if I can find two vectors in the plane making up this triangular face right here, their cross product will give me a normal vector. Well, the two vectors I could use are the vectors with initial points at the origin and terminal points at these two vertices right here. I can see that if I construct vectors out of these edges of the tetrahedron, both of them lie in that triangular face right there. Not only that, they're already set up as position vectors because their initial point is at the origin. So that means if I want a normal vector for this plane, I'm going to be taking the cross product of 1, 0, 1 with 0, 1, 1. I, j, k. 1, 0, 1, 0, 1, 1. Okay, that gives me, if you work this out, it's going to give me negative I minus j plus k, or in component form, negative 1, 1. That's the normal vector for my plane. To come up with the equation of this plane, I can use the point normal form for the equation of a plane using this normal vector and the point 0, 0, 0, which I know lies in the plane. And that's going to give me this equation for it. Negative x minus y plus z equals 0. But remember, I want this plane to be a bound for my function z. So I should solve this for z, giving me z equals x plus y. That's this face right here, z equals x plus y. That gives me bounds for my z, or limits of integration that I'll end up using for my z. So I'm going to say that z, remember this is the lower bound. Z is between x plus y, and the upper bound, that plane, is 1. Okay? Now what I want to do is describe this region D, which I'm going to do by looking at this sketch of D right here. So D can be thought of as either a type 1 or a type 2 region, but I'm going to think of it as a type 1 region since I already have Y isolated here. So D is the set of all xy such that x is between 0 and 1, which I can see here. Y has a lower bound of 0 and an upper bound given by this function here, 1 minus x. Okay? This I can use to rewrite the set T that I gave up here to give me limits of integration for x, y, and z. So let's rewrite the set T. X, y, z is the set of all x, y. It's the set of all x, y, z such that x is between 0 and 1. Y is between 0 and 1 minus x. And then finally z, as we found out up here, is between x plus y and 1. Okay. This is all the time that I have in this video. I do want to point something out about this. Triple integrals are a lengthy process, as you're already seeing. We haven't even touched the integral yet. All we've done is come up with the limits of integration. But I will say that for most examples, probably the hardest part of these problems is this initial setup, determining what this set should look like, which gives us our limits of integration. The integrals can be a little bit ugly sometimes too, but usually it's just a lot of kind of tedious work and not necessarily difficult work. But I would argue that this is probably the hardest part of a problem like this. So we'll finish this one up in the next video.